In this tutorial, I'll guide you step by step on how to create a VPC using plain Terraform code. Next, we'll refactor it into a well-structured Terraform module by following best practices. Finally, we'll make use of Terragrunt's top features to set up your infrastructure. We'll not only build a VPC module, but also create EKS and Kubernetes Addons modules from scratch. With Kubernetes Addons module, you can easily enable managed add-ons like CSI storage driver or self-managed add-ons such as cluster autoscaler, load balancer controller, Argo CD, and others deployed as Helm charts. In this tutorial, you'll learn many valuable techniques and best practices for creating Terraform modules, even if you don't end up using Terragrunt in your projects. Towards the end, I'll demonstrate a production-ready setup that includes using S3 bucket and DynamoDB table to log the state, as well as creating IAM role that can be assumed by users or automation tools like Jenkins. Additionally, we'll set up separate Git repositories for the live infrastructure and Terraform modules to help maintain a well-organized and efficient workflow. Terragrunt offers many useful features that can enhance your workflows. One such feature is ability to execute and apply Terraform on multiple modules simultaneously, while also sharing output variables from one module as input to others. For instance, we'll create a VPC module and use private subnet IDs as input for the EKS module. Terragrunt can also generate backend configurations and provider configs, saving you from copy, pasting, and keeping your code dry. Many people, including myself, find Terragrunt extremely helpful and use it in production environments all the time. Let's get started. In this tutorial, we'll talk about various ways to organize your Terraform code. One method is to make environments folder containing separate folders for each environment, like dev for development. This environment is for testing new infrastructure and app features, and it's okay if things break. Next, you might have a staging environment where you test your apps before going live, sometimes called pre-prod. This more stable environment should resemble production, but might be smaller in terms of resources and cost, and so forth. If you want to use Terragrunt recommended approach, we'll refer to these environments as live environments or infrastructure live. This naming sets this folder or Git repository apart from other Terraform code and modules. The live label means you can treat this repo as a reliable source, and whatever is declared in those folders should be up and running. For your reference, I'll label this first approach as V1 when we set up our infrastructure using the basic Terraform code. Alright, let's begin by creating a VPC under the dev folder. We'll use this VPC later to deploy EKS cluster. First, we need to declare provider. There are several ways to authenticate with AWS. For this initial example, I'll stick to the default method, which uses either environment variables or default AWS profile. Later, we'll assume roles, and I'll explain the difference it makes when creating EKS cluster. Next, let's set some Terraform constraints. You should use version 1 or higher. When Terraform provision infrastructure, it needs a way to track what was created. This is called Terraform state, and we use backend configuration to decide where to store it. For testing purposes, we'll use the local backend, which is the default option, but we can adjust a few parameters. Later, we'll switch to using S3 bucket and DynamoDB table to log our state. This approach should be used most of the time, especially when working in a team, instead of relying on local state. Here we can set a path for storing the state file. Often this path will be in object store like S3 or Google Cloud Storage bucket. Additionally, we can set version constraints for the AWS provider itself. That's all for the provider configuration. Next, let's create a VPC. First, we need to assign it a seeder block. At this point, you need to make important decision. If you plan to peer multiple VPCs in the future, you should come up with unique seeder ranges beforehand. Many third-party add-ons for Kubernetes, like EFS storage driver, require DNS support. It's a good idea to enable it from the start, as it can save you a lot of time when troubleshooting issues later on. Lastly, let's add the name tag. You'll notice that we use environment prefixes, which is a common practice even if you have separate accounts for different environments. Next, we'll create Internet Gateway to provide internet access for public subnets. We need to attach it to VPC and add a name tag. Now, let's create subnets. We'll make 2 public and 2 private subnets. The seeder block for each subnet should be a subset of the VPC seeder block. Then choose the availability zone. For EKS, you need at least 2 different availability zones. Subnet tags are crucial, especially for EKS. First, add a name tag. Then include a tag indicating that EKS can use the subnet to create private load balancers. Add another tag to associate the subnet with EKS with a value of either owned or shared. You can create EKS cluster without these tags, but some components might not work as expected. For example, cluster autoscaler or carpenter will use these tags to auto-discover subnets for creating additional Kubernetes workers. Next, create another private subnet in a different availability zone. Remember, the cluster tag must match your EKS cluster name. For the dev environment, we'll create dev demo cluster. Now, let's create the public subnets. You'll want to enable assigning public IP addresses when virtual machines launch. Additionally, tag these subnets to allow EKS to create public load balancers. Public load balancers get public IP addresses and used to expose your service to the internet. For example, Nginx Ingress Controller can create a public load balancer. In contrast, private load balancers only get private IP addresses, allowing you to expose your service only within your VPC. Finally, create the last public subnet in a different availability zone. Next, we need to create a NAT gateway to provide internet access to private subnets. I recommend manually allocating a static public IP address, as you might need to whitelist it with your clients in the future. It's better to allocate multiple public IPs in case you need to perform blue-green deployments. For the NAT gateway, we must explicitly depend on the Internet Gateway. Additionally, the NAT gateway must be placed in one of the public subnets with the Internet Gateway. Finally, we need to create routing tables. For now, both public and private subnets have the same default route, which is limited to your VPC only. First, we'll create a private routing table and use the NAT gateway as a default route. A route that uses all IP addresses is called the default route. Then, the second public routing table will have the default route set to the Internet Gateway. Next, we need to associate all 4 subnets, 2 private and 2 public, with the corresponding routing tables. In the next example, we'll dynamically generate subnets and associate them with routes. That's pretty much it. Optionally, you can expose VPC ID. This can be useful if you use it as input for another Terraform code or a module. That's all for the VPC setup. The current folder structure consists of live folder followed by the environments and component-specific Terraform code, such as VPC. Now, let's switch to the VPC folder and initialize Terraform. This will download all the required Terraform providers and initialize the Terraform state. Then run apply and enter yes to create your VPC. It may take about 2 or 3 minutes to complete. Once Terraform finishes, it should return the VPC ID. Now, you can check AWS console to confirm that we have a newly created VPC with a proper name tag and all 4 subnets with a dev prefix. This is a typical example of how to use Terraform to create AWS VPC. It's a very straightforward. Define in the code what you want to create and apply Terraform. The challenge is reproducing this at scale and keeping the Terraform code dry. Don't repeat yourself. Additionally, based on your backend configuration, Terraform will create a static file under dev VPC folder. If you want to reproduce this setup in another environment, such as staging, using just plain Terraform code, we'll need to copy the VPC folder to the new environment and replace all the environment-specific references. For some, we can use variables, but for others, such as backend configuration, we cannot. First, let's remove the state folders and file. In the backend block, variables are not supported and you'll have to manually replace the path for each new environment. For example, replace dev with staging. If you use a separate bucket for each environment, you'll need to replace the bucket name instead. Then we need to find all the references to the specific environment and replace them with staging. You can definitely use variables here. Under subnets, we have a lot of references to dev that we need to replace. I'll use Visual Studio shortcut to replace all occurrences of dev. Next, update NAT gateway and routes. It's possible that we may miss something, so let's search for the remaining dev references. Also, don't forget to update Internet Gateway. So far, our directory structure looks like this. That's it. Let's go ahead and initialize Terraform in the staging VPC folder. You may encounter an error since we copied the Terraform folder. To fix it, just run reconfigure, but be very careful and first ensure that you're in the right place. Then apply the Terraform. Alright, now we have one VPC for the dev environment and another for staging. The same applies to the subnets. We have 4 for dev and another 4 for staging. Some companies may choose to dedicate a separate AWS account for the production environment with a very limited access. Additionally, we now have another Terraform state file for the staging environment under the staging folder. In the following example, we'll improve it. But before proceed, make sure to destroy the staging and dev VPCs. Once completed, you should not have any VPC in that account besides maybe default VPC. By the way, you should not use the default VPC in any situation. It's only there for demonstration purposes, so feel free to delete it. Sometimes you may get an error that the default VPC does not exist, but it's a good sign that you forgot to update something. In the next part of this tutorial, we'll transform our Terraform code into a module. This will greatly reduce the amount of code we need to duplicate when working with different environments. By doing this, we're taking the first step toward making our code more efficient and less repetitive. At the moment, we'll keep everything in the same repository and create a folder specifically for the infrastructure modules. In the future, we'll explore how to structure Terraform modules across different Git repositories. Now, let's copy the entire VPC folder and place it under the modules folder. We can remove the dev folder, which contains the Terraform state and log files. Next, we'll begin refactoring. We don't need to declare provider within the module. Instead, we can just set version constraints for Terraform and provider. Let's remove the provider and backend configurations. Provider and backend will be managed in the infrastructure live folder. Next, create a variable file. We'll modify our code by moving some parts into the variables. One commonly used variable is environment variable. This helps differentiate between different environments and is often used as prefix for your infrastructure components. It's a good idea to add a description and specify a type like string for this variable. The next variable is a seeder block. In this case, we can set a default value for the variable and only override it when necessary. Now let's begin converting this code into a module following best practices. If there is no more descriptive and general name available, or if the resource module creates only one resource of this type, the resource name should be called this. Next, replace the hard-coded seeder block for the VPC with a variable. Whenever you create a module, replace all possible configurations with variables and provide default values if you don't want to change them. This approach will be helpful in the future if you receive a new requirements and need to update a parameter. It makes your modules flexible and future-proof. For instance, when working with DNS, you should also create variables and set the defaults to true. Now replace the dev prefix with the environment variable. You can also replace the entire name with a variable, not just a prefix. Next, apply the same process to the internet gateway. Replace the resource name with this keyword. Update VPC_ID to reference this as well. Also, update the name tag following the same approach used for the VPC resource. For subnets, let's remove the existing code and replace it with logic that dynamically creates subnets on demand. You can find similar logic in the official AWS VPC module. But first, let's add a few new variables. The first variable is for availability zones. We'll pass a list containing the zones we want to use. Next, create a variable for seeder ranges for the private subnets. Similarly, create another variable for seeder ranges for the public subnets. Next, create two more variables to pass additional tags for private and public subnets. This is particularly useful when using a VPC for EKS clusters, as previously mentioned. Now that we have variables for subnets, we can create Terraform code for them. Instead of using for each loop, we'll use the count variable and create as many private subnets as needed based on the input provided to the module. We'll then use the VPC reference. For the seeder block, we'll use the count index. We'll apply the same logic for the availability zone. For tags, we'll use built-in merge function to combine the provided tags with a name tag. Essentially, we'll use the same logic to create public subnets for the module. Now let's update the not Terraform code to use this keyword and modify the name tags to incorporate the environment variable. For the subnet, let's use the first generated public subnet. The same applies to the routes. We need to refactor the code and use this keyword. We should also update the logic to associate these routing tables with the generated subnets. Instead of hardcoding each route, let's use a count variable and the index of the subnets. First, let's associate a private routing table with all private subnets, and then do the same for the public subnets. Now let's add a few output variables such as lists of private and public subnets. These output variables can be used later when passing information to the EKS module. We can use star to return all created subnets. These shortcuts are simple but very powerful. We have now completed the module. Next, let's create another live environment where we can call these Terraform modules. We'll use the same structure, a dev folder for the development environment and another folder for the staging environment. Now create another VPC folder to invoke the VPC module. One crucial lesson learned from writing hundreds of thousands of lines of infrastructure code is that large modules should be considered harmful. In other words, it's not a good idea to define all your environments like dev, stage, prod, etc. or even a significant amount of infrastructure like servers, databases, load balancers, DNS, etc. in a single Terraform module. Large modules are slow, insecure, hard to update, challenging to code review, and difficult to test. Alright, create a main.tf file to call VPC module. First, as with plain Terraform code, we need to declare AWS provider and set up the backend. In this example, we'll continue to use local state. Next, declare VPC module. In this case, VPC is an arbitrary variable. Then specify the source. A Terraform module is simply a folder containing a bunch of Terraform code. You can reference it using a relative path or later on use a dedicated Git repository. Declare the environment. Since it's under the dev folder, it should be the development environment. Later, I'll show you how to dynamically obtain this information from the folder structure. Next, provide the availability zones, private subnet seeder ranges, and public ranges. Finally, let's pass the same subnet tags for both private and public subnets. As you can see, the code is now much more concise. We have reduced our Terraform code to a single file. Optionally, we can use output variables if you want to display them in the console. Otherwise, you can still use them, but they won't be printed to the console. To reference an output variable, first use the module keyword, followed by the module name and the module output variable. So far, we have VPC Terraform module and main.tf file under the dev environment to invoke it. Now, let's switch to the environment and initialize Terraform. After that, run Terraform apply to create VPC using this module. In the terminal, you can see all output variables such as subnets and VPC ID. Now, instead of copying the entire Terraform folder with all its files, we'll simply create another main.tf file under the staging environment. Let me copy the content of the main file from the dev environment and replace all the references with the staging keyword. Also, let's copy the output file. Switch to the staging VPC folder, initialize Terraform, and then apply the changes. Now we have the same setup as in the first example, a dev and staging VPC along with 8 subnets. Before moving on to the next example, let's destroy both the dev and staging VPCs. Alright, we have successfully deleted both VPCs. In this section, we'll improve our current setup by using Terragrunt. Terragrunt is a simple tool that offers additional features for making your configuration more efficient working with many Terraform modules and handling remote state. Let's make another live environment to use Terragrunt. To set it up, we need to create a Terragrunt file. If you're using the same S3 bucket and configuring a different path to store your state, you can place this file above your environment folders. You'll see more examples later. In this tutorial, we'll cover many features of Terragrunt. While most of them are simple shortcuts, when used together, they can greatly enhance your workflow. First, let's reorganize the Terraform backend configuration. Usually, you'll use remote state, but for this initial example, we'll stick with the local state. Keep in mind that backend configuration does not support variables or expressions, so you'll need to copy and paste it, updating the parameters as needed. For instance, even when using local state, you must update the path to the state file. For the development environment, it's dev/vpc/state, while for staging, it's staging/vpc/state. If you use different buckets, you'll also need to update the bucket name for each environment. Terragrunt helps you maintain efficient backend configurations by letting you define them just once in a root location and then inherit that configuration in all child modules. The path relative to include will be translated to dev for the development environment and staging for the staging environment. This way, you won't have to repeat yourself in the configuration. With Terragrunt, you can now create your backend configuration just once in the root Terragrunt file, and it will be used across all environments and modules. This simplifies your setup and reduces repetition. Managing provider configurations across all your modules can be challenging, particularly when customizing authentication credentials. If you need to update your provider, you must do so in each environment separately, which can be time-consuming and repetitive. Let's say you want Terraform to assume IAM role before connecting to AWS. You need to add a provider block with assume role configuration. You would then copy and paste this configuration into every one of your Terraform modules. While it's not a significant amount of code, it can be difficult to maintain. For instance, if you need to modify configuration to expose another parameter, for example session name, you would have to go through each of the modules and make the change, which can be cumbersome. In addition, what if you wanted to directly deploy a general purpose module such as that from Terraform module registry? These modules typically do not expose provider configurations, as it is tedious to expose every single provider configuration parameter imaginable through the module interface. Terragrunt allows you to refactor common Terraform code to keep your Terraform modules dry. I'll show you more examples later. For this basic example, we'll use AWS provider with the default authentication method and US East 1 region. That's all setup required to begin using Terragrunt. With this basic configuration, you can start taking advantage of its features to improve your Terraform workflows. Now let's create a standard folder structure for our environments, including dev and staging folders as usual. We'll also create a VPC folder to call the VPC module. To use Terragrunt, we need to declare a single file. Start by defining the source for the module, which can be a local path, a Git repository, or Terraform registry, just like a regular module source attribute. Here's where things differ. We'll include the root Terragrunt file that we defined earlier. This will generate backend configuration and setup provider for us. Then, under Inputs section, you'll provide the same Terraform variables that we used in the previous example, such as environment, availability zones, etc. This part is identical to a regular module, except that you need to use input block to supply these variables. To start using Terragrunt, you first need to install it. You can download it from the source, but a preferred method is to use a package manager. For instance, on Mac, you would use Homebrew to install Terragrunt. Next, navigate to the VPC folder within the development environment. Instead of running Terraform init, you just need to run Terragrunt init. You may want to create an alias for this command. Then execute Terragrunt apply. Once Terragrunt completes the deployment, you'll have the same VPC and subnets as before. Now let's examine the backend configuration. Terragrunt generates backend and profile configurations in its own working directory, which you can find under Terragrunt cache folder. You'll notice that we still have the dev key for the state. With the current setup, it's challenging to share your state with other team members, since the entire folder is ignored by Git. Now let's create a similar VPC in the staging environment. Copy the Terragrunt file from the dev environment and replace all references with staging. That's pretty much it. Navigate to VPC folder under the staging environment, initialize Terragrunt, and then apply the changes. Because we used the same backend configuration, Terragrunt created a different path based on the location, which starts with a staging key. This approach will be very helpful when working with remote backend configurations. As a result, we have the same VPC for both development and staging environments, along with the respective subnets. While it may not seem like a significant change, it can save you a lot of time and help maintain dry configurations when you have a large number of environments. Another useful Terragrunt feature is ability to run commands in multiple folders simultaneously. This will be incredibly valuable later when we define dependencies between modules. For now, instead of changing directories and running destroy to clean up, we can simply run Terragrunt run all destroy from the root folder. It will show you where it's going to execute those commands and ask for your confirmation. By running just one command, we have successfully destroyed both VPCs in the staging and development environments. In the following part of this tutorial, we'll make EKS Terraform module and add some extra features like cluster autoscaling. Let's move forward by making a new folder called EKS inside the infrastructure modules folder. We'll start by using the same version constraints for the AWS Terraform provider. Before we can set up EKS control plane, we need to create IAM role with EKS principal. After that, we must attach Amazon EKS cluster policy, which allows EKS to create EC2 instances and load balancers. For the cluster, we'll use environment variable and pass EKS name variable. Like in the previous module, it's a best practice to parameterize all possible options and set defaults rather than hardcoding them in the module or relying on provider defaults. Then attach IAM role to the cluster. We need to parameterize these values too. For now, I'll turn off the private endpoint since I don't have VPN in the cluster and enable the public endpoint. This way I can access EKS from my laptop and deploy applications. Up next, we have to supply subnets for EKS, which should be located at least in 2 different availability zones. Amazon EKS setups cross-account elastic network interfaces in these subnets to enable communication between your worker nodes and Kubernetes control plane. We'll pass this variable dynamically from the VPC module using Terragrunt dependency feature. That's about everything we need for the control plane. Now let's create IAM policy and IAM role for the Kubernetes nodes. We'll use a similar prefix for the environment and cluster name. If you want to set up multiple environments in the same account, you'll need to do the same, or else you'll face a conflict when trying to create another environment. Next, we have to attach multiple IAM policies to this role. We'll use for each loop to iterate over all provided policies and attach them to the node's IAM role. The last policy is optional. It allows you to use Session Manager to SSH into the node. In the next file, let's create EKS managed instance groups. As in the previous example, we want to iterate over all node groups provided as a map variable. All node groups must be connected to the EKS cluster cluster we created earlier. We'll use a key of the object for the node group, for instance, general. We'll also share the same IAM role among all node groups. If you need to grant additional access for applications running in EKS to the AWS API, you would use OpenID Connect provider instead. You'll see example of this later on when we deploy the cluster autoscaler. Next, we'll set capacity type of the node, which can be either on-demand or spot type. Then we'll specify the list of instance types associated with the EKS node group, such as T3A extra large. After that, we'll configure scaling settings. Remember that these settings only set up the initial autoscaling group parameters like minimum, maximum, and desired size. To enable autoscaling, you must deploy cluster autoscaler or use Carpenter. Next, we'll set up the desired maximum number of unavailable worker nodes during a node group update. I'll keep the default of one node at a time. It's also helpful to assign labels to the Kubernetes workers. Later, you can use node selector or affinity to bind pods with nodes. Additionally, we'll use a similar depend on statement to ensure that IAM role is ready before creating instance groups. The next step involves setting up OpenID Connect provider, which is used to grant access to the AWS API. Most of the time, you'll want this in your cluster, but sometimes it's not necessary. Let's create a Boolean flag called enable IRSA that we can use to create this provider on demand. Then you'll need to point it to the EKS control plane. Once you have retrieved the EKS TLS certificate, you can proceed to create OpenID Connect provider. Since we'll be creating additional Kubernetes add-on modules, we want to expose some variables that can be passed to another module. For example, the full EKS name that includes environment prefix. To deploy cluster autoscaler, we'll need to use OpenID provider IRN to establish trust between AWS IAM and Kubernetes service account. Finally, let's declare variables that we want to provide for this module. First, we'll use the same environment variable as a prefix. Then we'll specify the desired EKS version and the name of the EKS cluster. Next, we'll provide the list of subnet IDs that we want to pass to EKS, followed by the default IAM policies that we have to attach to the EKS nodes. Lastly, we'll define the node groups, specifying all the parameters of the desired Kubernetes node group. And finally, we'll add enable flag to create OpenID Connect provider. Now let's create another live environment, number 4. First, let's create a Terragrunt file and define shared objects between environments and modules. We'll continue using the local state for now, but this will be the last time, I promise. Also, we'll set up AWS Terraform provider with the US East 1 region. Next, create a dev folder for the development environment. Inside it, let's create another Terragrunt file, but in this case, define common variables only for this development environment. Later, when we need to create another environment, that's when you'll need to update most of them. For example, I want to share the dev environment prefix across all modules in this environment. Before we can create EKS cluster, we need to provision a VPC in your AWS account. Let's copy VPC module from the previous example and paste it under development folder. Make sure to delete the log and state files from the previous example as we don't need them. First, let's refactor the environment variable. Like in the root, we can include that environment variable in the code and use it whenever we need it. Expose attribute determines if the included config should be parsed and made available as a variable. Instead of hardcoding environment variable, we can dynamically pass it from the parent folder. This is another step to make your Terraform code dry. That's all for the VPC. We'll leave other variables as they are. If you decide to use a different EKS name, you must update the tags accordingly. Now create another folder for EKS module and make a new Terragrunt file. For the time being, we'll keep using the relative path to specify the module's source. Next, include the root to generate backend configuration and AWS provider, and then add a similar environment variable. By the way, you can also expose some variables in the root Terragrunt file if you want to share them between different environments, such as AWS account or region. Next, we need to provide input variables for the module. First, we want to use the most recent EKS control plane version available at the moment, which is currently 1.26. Then we'll use the same environment variable as in the VPC module and set EKS cluster name. This is where Terragrunt really shines. It allows you to define dependencies between modules. For example, EKS module depends on the VPC module and needs subnet IDs. With plain Terraform, you would have to use Terraform remote state and execute those modules sequentially. Next, we need to create a node groups variable with the desired settings for the group. Finally, define dependency on the VPC module. To do that, you simply need to point to the VPC folder where you invoke that module. It's also important to provide some mock outputs. This is helpful when you want to run Terraform plan on both modules simultaneously. If you omit this mock output variable, the plan will exit with an error stating that the EKS module needs subnet IDs. You'll see this in action soon. That's all for the VPC and EKS module. Now let's go ahead and initialize Terraform. Terragrunt offers another useful feature that allows you to run the same command in multiple folders and, most importantly, respect dependencies. Let's switch to the development environment. From here, we can run init for both VPC and EKS modules. By the way, it's optional. Terraform will automatically initialize it when you run plan or apply anyway. You can see that Terragrunt will run init in the VPC first and then in the EKS module, since we have defined dependencies. Now let's run plan. It will execute in the same order, VPC and then EKS. If you leave the mock variables out, the plan will exit with an error on EKS. Alright, we can run apply now. Terragrunt will show you the order again and ask you to confirm the action. When you say yes, it will create VPC first and use subnet IDs output variables as inputs in the EKS module. Typically, we have many different modules in our environments, and it becomes extremely helpful to share output variables and run apply on the entire environment simultaneously. Alright, it will take maybe 10 minutes to create VPC and EKS cluster. To access EKS cluster, we need to update our local Kubernetes config using AWS EKS command. Let's run kubectl get nodes to verify that we can connect to the cluster. At this point, we have VPC and EKS cluster set up. Most of the time, you would want to deploy additional components such as cluster autoscaler, CSI storage drivers, load balancer controllers, etc. For that, let's create a separate Terraform module called Kubernetes Addons. We'll combine managed and self-managed add-ons that are deployed as a Helm charts. As always, let's begin by creating a version constraints. In the case of this module, we want to use Helm provider to deploy self-managed Kubernetes add-ons as Helm charts. Next, let's create additional Terraform file for each add-on. The first one is the cluster autoscaler. The cluster autoscaler needs access to AWS API to discover autoscaling groups and adjust desired size setting on them. For that, we need to use IAM for service accounts. We'll deploy it in the kube system namespace, and the Kubernetes service account name is cluster autoscaler. We need to set it in the Helm chart later. All Kubernetes add-ons will have a flag to enable them, such as enable cluster autoscaler. If it's true, the count is 1, which means we'll create this type of resource. Then use EKS name as a prefix for the IAM role. Next, let's create IAM policy that allows cluster autoscaler to work properly as I described earlier. Attach this policy to trusted IAM role. And let's create a Helm release. It will also use a Boolean flag to enable it, the name of the Helm release, the remote repository to use, and the chart name. Specify the namespace, which must match the namespace on the IAM role. Then provide the chart version. Now it's important to match the service account name with the IAM role. To establish trust, we must set Kubernetes service account annotation with the IAM role run. Finally, provide EKS name so that the cluster autoscaler can auto-discover subnets and autoscaling groups. This functionality is based on the subnet tags that we provided earlier. Now, I intentionally limited the number of parameters that we can customize so that everyone can follow the same process and limit the drift between environments. To deploy load balancer controller, just create another Terraform file and follow the same logic. The same goes for Carpenter, Argo CD and other components. First, as always, environment variable. Then the EKS cluster name that we'll get from the EKS output variable, a flag to deploy the cluster autoscaler, the Helm chart version of the cluster autoscaler, and finally we need to pass OpenID Connect provider IRN from the EKS module. That's all for the Addons module. Next, create Addons folder under live development environment and create a Terragrunt file. As always, we need to define the source of the module, include the backend and AWS provider config, and then the same environment variable. Now we need to pass EKS name as a dependency from the EKS module and OpenID Connect provider IRN. Enable the cluster autoscaler, specify the version of the chart that we want to install, and define dependencies on the EKS module. Specifically, we need EKS cluster name and OpenID Connect provider IRN. The tricky part is to authenticate Helm provider, which will generate using Terragrunt as well. Keep in mind that you cannot pass variables from the EKS module here. This provider will be generated and can only use variables that provided to the module itself. Essentially, you can generate anything you want. To initialize Helm provider, you need to get a temporary token. You can pretty much initialize any provider that needs to authenticate with EKS using the same principle, such as Kubernetes and kubectl Terraform providers. That's all, let's go back to a terminal and run Terragrunt apply on the whole development environment. Since we define dependencies, you can see the order in which Terraform will apply the infrastructure. Let's confirm it. After deploying infrastructure with Terraform, it's important to verify that the cluster autoscaler has been installed correctly. To do this, you can check the installed Helm charts and confirm that the autoscaler is installed. Additionally, you should make sure that the autoscaler pod is up and running. It's also recommended to check the logs for the autoscaler for any errors. If there are any misconfigurations, you may see an error in the logs indicating that autoscaler is not able to access AWS API due to permission denied. If the autoscaler is unable to access AWS API, it won't be able to adjust the desired size property for autoscaling. Therefore, it's important to confirm that the autoscaler has been deployed successfully. To test if the autoscaler is working correctly, we can create a simple deployment based on Nginx with 4 replicas. After creating the deployment, we can watch the pods in the default namespace and see that one pod is in pending state. This is because there are not enough nodes to schedule the pod. We can describe the pending pod and confirm that autoscaler is triggered to add more nodes. We should see a message indicating that the pod triggered scale up from 1 to 2 instances. After a few seconds or minutes, a new node should join the cluster and the pending pod should be scheduled. This test confirms that the autoscaler is working correctly. To replicate the setup in the staging environment, you can simply create a copy of the dev folder and rename it to staging. The only required change would be to update the environment variable from dev to staging. While you can also update other local parameters such as EKS node instance types, since autoscaling is set up, the same setup can be used across different environments, including production. Switch to the staging environment and initialize. When we run plan, we may receive an error message, but let's run it again. The problem is that Helm provider requires existing EKS cluster, so we cannot fake it. If we still want to run plan on some folders and exclude add-ons, we can use a specific command. Alternatively, we can run the apply, which will work because add-ons module is invoked only after EKS cluster is provisioned. Overall, we have 3 groups in the execution plan. Great, we have successfully set up VPC, EKS cluster and autoscaler in the staging environment. To connect to the staging EKS, just update the name of the cluster in your Kubernetes config file. You can see that the cluster autoscaler is running in the kube system namespace. Now let's check our clusters on AWS console. Since we used environment prefixes, we were able to create 2 independent environments in a single AWS account. We now have 2 clusters, each with its own environment prefix. To destroy both environments, we just need to run destroy on the top level. Terragrunt will destroy both the development and staging environments at the same time. It will do so in reverse order, deleting the Helm charts, EKS clusters, and lastly VPCs. If you check AWS console, you'll see that all the clusters and VPCs have been removed. In this part of the tutorial, I'll teach you how to use Terragrunt for real-world projects. We'll separate our code using Git modules, save our remote state in S3 bucket and secure it with DynamoDB logging. Plus, we'll use IAM role to set up our infrastructure. First, we need to create S3 bucket to save the Terraform state. You can name it anything, but remember, it must be globally unique. It's also a good idea to turn on bucket versioning, so if something happens to your state, you can always go back to earlier version and recover it. Now let's create DynamoDB table to log Terraform state. This helps avoid conflicts when several team members try to run Terraform simultaneously. We'll name the table Terraform log table and create log ID partition key. That's all we need to manage the remote state in our S3 bucket. Instead of giving users direct access, we can create a dedicated IAM role for applying all infrastructure changes. This role can be assumed by users or, even better, by automation tools like Jenkins. For now, let's give the role admin access, as the specific permissions needed will depend on your infrastructure plans. We won't cover IAM permissions in this tutorial. Choose administrator access and add it to the role. Then name it Terraform. By default, any user in this account can potentially assume this role. We can limit this on principal side if needed, but it's not required, as we'll need to explicitly grant users permission to assume this role. In the next step, we'll create IAM policy that allows users to use this role. First, copy the IRN of this role. Then create a new policy allowing users to use the Terraform IAM role and name it Allow Terraform. Following best practices, let's avoid attaching the policy directly to users. Instead, create IAM group called devops and add Allow Terraform policy to this group. For the demo, create a new IAM user and add them to the devops group. This will allow the user to assume Terraform role. Keep in mind that any user with admin access in the account will also be able to assume the Terraform role. Next, generate security credentials for the user. We'll use these credentials to create AWS local profile. Download credentials. Now you can use AWS configure command to add a new profile for the user. Next, create a separate Git repository to store your Terraform modules. You have two options: store all modules in the same Git repo or create a separate Git repository for each Terraform module. With the last option, you might end up with many repositories which can be difficult to maintain. If you just starting out or have a relatively small DevOps team, begin with a single repository. Name it infrastructure modules. Make repository private, add README file, and include a git ignore file for Terraform. Now clone infrastructure modules Git repository and open it with a text editor. First, let's copy VPC Terraform module we created earlier. Add this module to Git repo and commit the changes. When using a single Git repository for multiple modules, create a Git tag specific to this module so we can reference it later. If you need to make any changes to the VPC module, commit again and create a new VPC tag. Finally, push the Git tags to GitHub or another remote Git server. So far, we have a single tag in the GitHub repository. Next, let's copy EKS module. Follow the same workflow, add it to the repo, commit the changes, and create a new Git tag specific to this EKS module. Finally, let's move Kubernetes Addons module to the infrastructure modules Git repo. Add it to the repo and create a new tag. This is the last module we're going to add. Now we have 3 separate Git tags related to specific modules. That's how you manage multiple Terraform modules in a single repo. Next, create a new Git repository to store the live state of our infrastructure. Make the repository private and select Terraform for the git ignore file. Clone this new repository as well and open it in Visual Studio Code or your preferred text editor. First, create a root Terragrunt file. In this case, we'll use a remote S3 bucket to store our state. Since we're using IAM role to apply changes, we need to provide the IAM role IRN and specify the profile that can assume that role. Then provide S3 bucket and finally DynamoDB table to log the state. Next, let's generate AWS Terraform provider. We'll also use the same role and AWS profile to run Terraform. Optionally, you can give the provider a session name. Now, let's copy development environment from the previous example and make a few adjustments as it won't work out of the box. First, let's clean up by deleting previous local state and log files from all modules. Next, we need to update the source of the modules to point to the remote Git repository and use tags to pin each module to a specific version. Let's update the Kubernetes Addons source first and then the VPC module. This example is taken from Terragrunt Quick Start. Additionally, we must update the Helm provider to use a token. I'll explain why later. We also need to ignore Terragrunt cache. Now switch to the development environment and run Terragrunt apply. It will show you the order in which the modules will be applied and ask for confirmation. It seems that Terraform was updated and no longer supports github.com as is. We need to update this in the code. Let's go through all three modules and add git schema before each module, the Kubernetes Addons module and finally the VPC module. Run the command again, confirm that you want to update the state, and in a few minutes Terraform should create VPC, EKS cluster and deploy Autoscaler. Now you can check S3 bucket and find that a dev key and separate paths for each module, VPC, EKS and Kubernetes add-ons. Let's try to connect to the cluster as we did in the previous example. We now get the error even when we're using the default AWS provider with admin access. We don't have permissions to access Kubernetes. The problem is that only IAM user or role used to create the cluster has access to it. I have a separate video on how to add additional users and IAM roles while following best practices. For now, let's create a new AWS profile for the Terraform IAM role. This indicates that Anton user will be used to assume this Terraform role. Next, update Kubernetes context once again, but this time use Terraform profile. Now we can access the cluster. Let's also check if the Autoscaler is running. To destroy all infrastructure, just run destroy in the dev environment. The next step is to add additional users and learn how to use Argo CD to deploy applications to Kubernetes. Thank you for watching and I'll see you in the next video.